Hello. In this video I'm going to work through two solutions to associated questions 56 and 58 concerning a locomotive's adhesion and arrival times. I'm going to work through them both by hand and show you methods using the calculator. Okay, so here's the first question. We're told that this locomotive has something called adhesion, which follows a normal distribution with a mean of 0.37. We also know that its standard deviation is 0.04. The first part of the question asks us to find the probability that the train has an adhesion of at least 0.30. So 0.30 is way down here, way more than one standard deviation below the mean, and we want to know the probability of it being greater than 0.30. There are several ways we can do this. First, I'll show you using the table. First, we're asked to find out the probability that the adhesion is bigger than 0.30. We then need to standardize that, and we standardize that to a z-score by working out value minus the mean over the standard deviation, and that's minus 0.07 over 0.04, which is minus 1.075. So I want the probability that z is bigger than minus 1.75. We can have a look at the tables, but the tables tell us the probability of being lower than a value, and we want the probability of being greater than a value. So if we have a look at minus 1.75, we find it right in the middle here, and it's 0.0401. So we want 1 minus that, which is 1 minus 0.0401, and the answer is 0.9591, or 95.91%. We could have done this directly on the TI. Second vars to get distributions. Then we want the normal CDF. We can see right here on the screen lower tail of a very, very, very large negative number, upper bound of 0.3, mean of 0.37, standard deviation of 0.04, and we see that it gives us an answer of 0.04006, which corresponds with the table precisely. So both methods confirm that the answer to part A is that 96% of the time the locomotive will arrive at its destination on time. Part B is asking for the probability that it will be too early, and this is if the adhesion is greater than 0.5. So as before, got the normal distribution, the mean is 0.37, standard deviation is 0.04, and we want the probability of it being bigger than 0.5. So we're looking for this very, very, very top tail. The probability that x is bigger than 0.5 is going to be the same as the probability that z, standardizing, is greater than the value minus the mean over the standard deviation, which is the probability that z is greater than 0.13 over 0.04, which is the probability that z is greater than 3.25. We already know this is going to be very far away from the mean, so it's going to be a very small number. Again, the tables tell us the area less than, so we want 1 minus this. So we want to look up 3.25 in the tables and take 1 minus that. So 1 minus phi of 3.25. Looking at the tables, we see that it's all the way over here, and we can see that the whole row virtually corresponds to 0.9994. So it's 1 minus 0.9994, which is of course 0.0006. So 0.06% of the time this train will arrive too early. We could have done it on the calculator. Let's do it directly from the original data. Second vars, normal CDF. This time we want a lower limit of 0.5 and an upper limit of a very large number. So let's say it's 50. The mean is 0.37, sigma is 0.04. 6 times 10 to the minus 4, which absolutely corresponds with our answer. So the final question says compare the answers to parts A and B. Does it make sense to make one of these larger than the other? Well, part A was the probability of arriving on time. Was 95.91%. Probability of arriving too early was 0.06. 95.9% of the time is obviously very good. It would be great if it was a little bit better than that. So I believe it makes sense to have the arrival probability to be bigger than 96%, which we have now, and the probability of arriving too early, which normally wouldn't be a problem, but in this case it says that if it does arrive too early at a switch point, it does cause problems, so we want that one to be smaller. So we want the arrival time to have a bigger probability and the too early time to have a smaller probability. That is question 56. Question 58 still has the same information. We're using the same mean and variance as before, but this time we're asked to figure out whether it makes more sense to change the mean or change the standard deviation to have the proportion of late arrivals less than 2%. Well, right now we know that if it's greater than 0.5, it's arriving too early. If it's greater than 0.3, it's arriving on time. So the probability of arriving too late must be the probability that the adhesion is less than 0.3. So the first question asks, what would we have to change the mean to have this bottom tail only 2%? We need to find out what z value is associated with a bottom tail of 2% would be the first thing. We know it's going to be a negative z value, so we're going to try to find 2% in the table, so 0.02 in the tables, and we actually find it right in the middle here between minus 2.05 and minus 2.06, and it's about midway through. In fact, if you think about it, 202 and 197, this is 2 over, this is 3 below, there's a whole gap of 5 here, and we want to do 2/5 of the way through this interval. So interpolation suggests that the answer to this is minus 2.054. Part B says if we keep the mean at 0.37, how much would we have to reduce the standard deviation to have the 2%? As before, we know that the 2% cutoff needs to be 2.054 standard deviations below the mean. We know that this is 0.3 and we know that the mean is 0.37, so this gap of 0.07 needs to correspond to 2.054 standard deviations. So 0.07 equals 2.054 standard deviations, and we just divide and we get that the standard deviation needs to be 0.034. Part C asks us to consider which of these two options is preferable, and it gives us a clue that we should consider the effect on the probability of arriving too early. So the probability of arriving too early is the probability that the adhesion is bigger than 0.5. So in part A we had x follows a normal with a mean of 0.382 and the standard deviation of 0.04. If we do this by standardizing, we get the probability of being bigger than 0.5 is the probability that z is greater than 0.5 minus 0.382 over 0.04, which gives us the probability that Z is greater than 2.95. And 2.95 gives us 0.9984. So 0.9984 is the main body area, so we want 1 minus that. 1 minus 0.9984, which is 0.0016. So the probability that the train arrives too early is 0.0016. Whereas in part B, we're told that x follows the normal with the same mean as before, 0.37, but this time the standard deviation has been reduced to 0.034. And again, the probability that x is bigger than 0.5 is now the probability that z is bigger than 0.13 over 0.034, and that turns out to be 3.82 standard deviations. If we go to the tables, we note that 3.82 isn't even listed on the tables. It's so unlikely. We're already way beyond 0.9998. So according to the tables, this probability is minuscule and negligible. If we do this on a calculator, we'll have the lower bound of 0.5, the upper bound of a very large number, 50, mean is 0.37, and we'll have standard deviation of 0.034, and we get an answer of stupidly small, 3 times 10 to the minus 5, which corresponds to being so unlikely that it's out of the table. So it's 0.00003. Therefore, B is by far the better solution, to leave the mean the same and try to lower the standard deviation. Thank you.